Alright, so I'm going to summarize Sn2 mechanism quickly. I'll try to do that. So Sn2 mechanism is substitution mechanism done to alkyl halides, and alkyl halides are carbons that are connected to any halogen. Halogen will represent by X, and it could be chlorine, bromine, iodine, etc. So looking at Sn2 mechanism, this is a mechanism that is a second rate law. Those are the kinetics, meaning that both the substrate and the nucleophile will affect the rate of the reaction. So they both are important. Let me show you just the general reaction, what actually happens, and this is a single step reaction. So we have a nucleophile, and it should be a good nucleophile, and we have our carbon connected to some halogen, and let's say we have something here and something here and something dash here. Now this is not methyl, so don't take that as CH3. Let's just call it H, H, and H. Now this carbon is methyl connected to a halogen. So this is very good and favorable for our Sn2 mechanism. I'll explain later. There is a substrate relationship, and this halogen is actually our leaving group. So it's abbreviated LV, leaving group. Even better, LG. And what actually happens? So first of all, this bond breaks, and the electrons, 2 electrons, are given to the halogen. On the nucleophile, we have our electrons coming from the back side of the carbon and actually forming a bond. And what it does, it actually flips the carbon, like if you think about an umbrella that is being winded, so it actually just flips. So what you will get in this case will be actually the carbon, the nucleophile connected to the carbon, and hydrogen, hydrogen, and hydrogen. So as you see, it's just flipped, came from the back and flipped the carbon. So this is the general reaction, what happens, and the rate for this reaction, which is second order rate. So that means we have our rate constant times our substrate, and that is times our nucleophile. So this is our rate law. Now what actually affects Sn2 mechanism? So there are actually 4 things that affect the mechanism. First thing that is really important is actually our substrate. Now the substrate should not be hindered. That means that there shouldn't be too many groups around the substrate, and the reason for that is when we form the transition state, the more groups we have, the more unstable the transition state, and I'll explain. So the substrate could be either first, it could be methyl, like I showed on top. It could be first, it could be second, and it could be third. And what does that mean, those first, second, and third? That means that we have our carbon halogen bond, and to this specific carbon we could have either one R group connected and the other are hydrogens. Second could be again CX, and we have 2 R groups hydrogen, and the third one will be 3 R groups. So those are the substrate options. And let me just give you an example. If we have this substrate, so what is the number here on this carbon? Because we look at this one because it's the one that is connected to the bromine, the halogen. So if you guessed it right, as you can see, it is connected to only 1 R group and it has 2 hydrogens, so that means it's a first order. Alright, so we have those 3, first, second, and third, and methyl of course. And now let's see how they affect the Sn2 mechanism. So as I said before, it has effect on the transition state. So we need unhindered substrate, meaning that the first substrate is the best. Of course methyl is the best, but let's call the first is the best. Methyl will be even better, but we'll go first compared to the second compared to the third. Now first is best, second could give you Sn2 reaction, third will not give you no Sn2. And the reason for that is I'll show you the two examples. So let's take first here and third here. So here, as you see, this is our third one because this carbon connected to 1, 2, 3 R groups, and here we'll do 1 because this connects only to one R group. In both cases we will use the same nucleophile, so it will be OH minus, a good strong nucleophile. And of course it won't be OH minus, it will be probably some salt like NaOH, because we cannot have charged in our flask. And what actually happens in the mechanism? So both cases it's a one step. Bond breaks, gives the electrons to the Br, to our halide, and the nucleophile, the 2 electrons coming from the backside and binding for the carbon. So now the more important thing, let's check the transition state of both cases. Transition state in this case, if you would see, will be the bromine bond breaking, partially negative, and here we have a bond forming of the hydroxide. And of course, you know, according to this, we have here 2 hydrogens. Now here, what happens? We have the bond breaking, partially negative, bond forming, partially negative, and we have the group. Now if you look at this case, the carbon over here is overcrowded. We have 1, 2, 3, 4, 5 things bonded to it, so it's very unstable and unfavorable, meaning the reaction won't happen here. The other case, the carbon here still have space and could go forward. That's why this reaction is more favorable, and this will give you the result, which the result will be just OH. So we substitute our bromine with the OH. Okay, so we just covered substrate, which is an important part to it, very important part. So it's good to know that the substrate affects the results. Now let's go to the second thing that is affecting is our leaving group. So the second thing is leaving group. Leaving group is very important as well. We need to have a good leaving group is needed, and good leaving group is actually a weak base. So like halogens like fluorine and bromine and iodine are good leaving groups because they are weak bases. OH is not a good leaving group. Fluorine is not a good leaving group. So when we look at leaving group, we need a good leaving group, a weak base. Very important. Second thing that we should take in mind in those 4 things is our nucleophile. So the nucleophile is this thing that comes and substitutes our halogen. And third thing, nucleophile. And the nucleophile should be a good nucleophile. What does it mean, good nucleophile? Strong bases are better nucleophiles. So if we look at HCl and OH minus, so although HCl is strong, HCl is actually a strong acid, so it's not a good example. Let's do this. So it will be CH3OH. Both of them are bases, but this is a stronger base, including it has a charge. So if it has a charge, it'll always be stronger than this one. But we're looking at a strong base, and the nucleophile is actually increasing when we go down a column in the periodic table. And as I said before, negative charge will always be a stronger nucleophile. This is the third thing that we look at when we look at a Sn2 reaction. Now, the third thing that we should consider is our solvent. Now solvent is important as well, and for an Sn2 reaction we need a polar aprotic solvent. What does aprotic mean? It means it's polar, it's a dipole-dipole, but no hydrogen bonding. So a good one could be acetone. Acetone. A bad one could be anything with hydrogen bonding, so it could be water. So the reason why we need aprotic is because we have such a good nucleophile that we don't want it to be surrounded by hydrogen bonding and actually enclosed and not letting it react. So we want it to still be open, and that's why we use aprotic. So those are the 4 things that we should consider when we're looking at Sn2 mechanism. I hope this was helpful, and I will put an example of a question that I'm solving.